To understand how a user experiences a website, the software industry relies on a standard playbook: capture the user's screen, record their face, track their voice, and send all of it to a remote server for analysis. That architecture immediately creates a strict boundary. Sending real-time biometric data and screen captures to off-site servers is entirely unworkable for hospitals, financial institutions, and government agencies. The privacy risk stops the conversation before it starts. But the deeper flaw in these tools happens after the data arrives. They ingest highly complex, disparate metrics, like how hard a user is thinking, where their eyes move, and whether the code is broken, and they mathematically collapse them together. The output is a single, opaque health score, say a 90 out of 100. It creates a metric of false confidence. Averaging deterministic software errors with subjective human emotion hides the actual friction. A perfect technical score can easily mask a highly stressful, frustrating user experience. AffectEQ is built as the engineering counter-approach to this problem. Looking at their core philosophy, the platform processes all data locally on the host machine, strictly refuses to average the metrics, and explicitly reports its own failures to the user. True intelligence about user experience requires a verifiable chain of evidence, rather than black box guesses disguised as definitive scores. The system architecture began with a rigid constraint: execute complex, multimodal AI analysis entirely on the local device, with zero internet loopback. To see how that works in practice, we start at the top of the raw data funnel with the facial tracking engine. The hardware pole maps 478 three-dimensional facial landmarks, tracking them 30 times every second. That massive stream of raw input is fed immediately into 9 distinct neural networks, all running natively on the user's machine. This technical diagram details how those models calculate facial muscle movements, head pose, gaze direction, and mouse behavior. Together, they generate roughly 550 individual signals during a single session. Standard analytics tools would immediately blend that data together. AffectEQ forces the signals to stay separate. The system routes the data through strict validity gates. A specific signal is only passed forward to the 4 evidence axes if the models can mathematically verify its integrity. By isolating the data at every stage of the funnel, an engineer can look at any final metric and trace it back to the exact code or physical movement that created it. The platform divides this verified data into 4 lanes. This first panel details the deterministic audit. It applies 110 strict code heuristics to read the page without relying on AI at all. The second axis is the AI visual review. It uses an 8 billion parameter vision language model, running locally, to look at the screenshots and critique the layout's design. The final 2 axes analyze the user directly. Live human affect categorizes 7 different emotions, while the cognitive load axis fuses blink rates, muscle effort, and behavioral struggle to measure how hard the user is working. The defining rule of the entire architecture is that these 4 lanes are mathematically walled off from one another. The code itself prevents an aggregate number from being generated. The field for a composite score is set to null, permanently. This matters in practice because a website's codebase might be perfectly optimized and score well on a technical audit, while the actual layout induces massive cognitive load in the person trying to navigate it. Forcing that composite score to stay null ensures teams have to confront conflicting data points, rather than letting a fake average hide the problem. Technical buyers share a common skepticism about vision language models. They frequently hallucinate findings that aren't actually on the screen. To counter this, AffectEQ uses a hallucination guard. Every raw observation the AI makes must be cross-checked against the actual elements on the live page. If an observation cannot be grounded in the page's reality, the system throws it out. It then explicitly displays the exact percentage of data it dropped to the user. That same restraint applies to system failures, governed by a protocol called honest degradation. If a local AI model crashes mid-run, or if the camera doesn't capture enough data to establish a baseline, the tool does not guess. It simply outputs a message stating that the lane did not complete. A calibrated competence metric requires a tool to be hard-coded with the ability to say, "I don't know." The result of this architecture becomes clear when looking at the output from a live human session. This participant dashboard displays a standard 5-minute run. Over 3,000 discrete frames of biometric data were processed. The emotion timeline runs perfectly parallel to the cognitive load metric, fusing behavior, gaze, and effort into a single synchronized view. But even here, the system exercises strict restraint. It tracks the user's heart rate using facial color variation, but it deliberately excludes that heart rate data from the cognitive score. It labels the metric as a preview because it hasn't passed the threshold for full validation yet. All of this dense, synced biometric intelligence is generated natively. Not a single packet of data leaves the operator's laptop. The dashboard proves that measuring user experience with multimodal AI does not require offloading your data to a cloud cluster. Building an entirely local system is a structural necessity that creates a hard boundary in the market. This exact architecture is mandatory for environments bound by GDPR or operations working in healthcare, finance, government, and defense. Traditional UX tools are legally locked out of these verticals because their data flow requires third-party servers. AffectEQ has taken the highly subjective practice of measuring user experience and subjected it to rigorous engineering standards. By designing a system that mathematically refuses to fake what it cannot prove, technical teams finally have access to UX data they can actually trust.